If I asked you what makes a modern microchip fast and reliable, the engine inside your phone or a massive data center, you'd probably say something about faster transistors.
Or maybe nanometer scale lithography. And I mean, those things are incredibly important.
But they hide a much deeper, more fundamental problem, don't they?
They do. It's not just about making things smaller, it's about managing the relationships between billions of components. When you're working at the angstrom scale, distance isn't just distance.
Proximity becomes everything. It's the line between a chip that works and one that completely fails.
Exactly. And the design problems are so complex, they're computationally exponential. If you tried to just brute force a solution,
You'd run out of time before the chip was even built.
yeah,
Yet somehow, these things get designed every single day. So how?
the answer comes from, well, a surprisingly elegant geometric tool. It's called the Voronoi diagram.
A map.
Essentially, yeah, it's a map of influence, a map of nearness, and it turns those impossible computational problems into efficient geometric ones.
So our mission for this deep dive is to explore that hidden geography of the microchip. We want to understand how mapping nearness lets engineers build the faster, smaller, and more reliable systems we depend on. Okay, let's unpack this. And to do that, we have to start in a, frankly, bizarre geometric world.
A world where the normal rules of distance just don't apply.
Right. When you or I think about distance, we think of a straight line, point A to point B.
That's Euclidean distance as the crow flies. But inside a chip, a very large-scale integration or VLSI chip, you can't fly
Why not?
because of the physics of photolithography. The wires, the little electrical traces, can only be laid out in perfectly horizontal or vertical lines.
Just on a grid.
A completely rigid grid, you just never see a diagonal wire. So if a signal needs to get from one corner to another,
You can't take the shortcut, the hypotenuse,
no, it has to follow the grid. It has to take a path made of right angles.
which gives us the perfect analogy, the Manhattan metric.
Yes, the L1 distance. It's literally the distance as the taxi drives along the grid. You add up the horizontal distance and the vertical distance.
That constraint, that physical reality, is non-negotiable, right?
It's the absolute foundation. And if your physics is built on that metric, your data structures, the way you organize the billions of components, had better be built on it too.
So historically, how did engineers try to organize all this spatial data?
Well, the standard tool for a long time was something called a KD tree, a K-dimensional tree.
This is pretty advanced.
And it was for a lot of applications. The way it works is it recursively carves up the space. It'll take the whole chip area and cut it in half along the x-axis.
Okay.
Then it takes each of those two new boxes and cuts them along the y-axis and so on. You get this neat little hierarchy of rectangular boxes.
That sounds really efficient for searching, for indexing things. But you're about to tell me there's a huge flaw.
A fundamental structural deficit. The problem is that those cuts, those boundaries, are completely arbitrary. They're based on coordinates, not on physical reality.
What do you mean?
Imagine two parallel wires running so close together, they're electromagnetically interfering with each other. I mean, fractions of a nanometer apart.
Okay, a huge problem for signal integrity.
A huge problem. But what if the KD tree's arbitrary dividing line happens to fall right between them?
Then those two wires, which are basically touching, end up in completely different branches of the data structure.
Exactly. The algorithm knows which box a wire is in, but it has zero understanding of who its true physical neighbor is.
So if you ask the most important question, who is closest to this wire? The KD tree has to what?
It has to backtrack, it has to check the box it's in, then it has to check all the neighboring boxes and their neighbors. It completely defeats the purpose of the index.
You've created this massive organizational system that fails at the one thing that matters most on a chip.
Proximity. The KD tree knows about coordinates, the chip runs on physics. And that mismatch creates enormous wasteful overhead.
So if the old way failed because it was just about coordinates, the solution has to be a map that's only about proximity.
And that is the Voronoi diagram. It is fundamentally a map of nearness.
How does it work?
You take a set of points, we call them sites, and you divide the entire plane into regions or cells. The only rule is this. Every single point inside a given cell is closer to that cell site than to any other site on the entire map.
I think the classic post office problem makes this really clear.
It's a perfect analogy. So You're in a new city, you need to find the closest post office. The inefficient way, the KD tree way, is to measure your distance to every single one.
A linear search. It's slow.
Very slow. But if you have a Voronoi map of the city's post offices, the map is already divided into these regions of influence.
You just find out which region you're standing in, and you instantly know which post office is closest.
It turns a slow search into basically an instant lookup. And what's so powerful is that this has always been about revealing hidden spatial influence.
You mentioned a historical case that really drives this home, that this isn't just some abstract math.
Absolutely. In 1854, the physician John Snow was trying to figure out a cholera outbreak in London. He mapped where all the deaths were occurring. And when you look at his map, it's a Voronoi diagram. He realized that the deaths were almost all contained within the Voronoi cell of a single contaminated water pump on Broad Street.
So the map wasn't just showing addresses, it was showing the invisible zone of influence of the contaminated water.
Precisely. It proved the disease was waterborne, and that exact power mapping influence, not just coordinates, is what was needed for the microchip.
Okay, that's a brilliant insight, but we immediately run into our old problem again. The standard Voronoi diagram, like the John Snow map, uses that as the crow flies Euclidean distance.
Right. And if we use that, we're right back to ignoring the physical grid of the chip. The math and the reality are out of sync again.
So you have to adapt the tool.
You have to make the tool speak the language of the chip. And that gives us the rectilinear Voronoi diagram, sometimes called the L1 Voronoi diagram.
The same principle, different ruler.
Exactly. It still partitions space based on the closest site, but it defines closest using the Manhattan distance metric.
And changing the metric must completely change the geometry of the map itself. The boundaries between cells in a normal Voronoi diagram are straight lines.
They are, but in L1 space, the bisector, the line of points that are equidistant from two sites, is no longer a straight line at all. It becomes this complex staircase-like path.
The staircase, that seems so counterintuitive.
It seems that way, but think about what it represents. That staircase path, made of segments at 45 and 135 degrees, is actually modeling the way a signal has to travel on the grid.
Ah, so it's the perfect fit.
It is the perfect fit. The boundaries of the map now perfectly align with the physical constraints of the chip. You've gone from an arbitrary box from a tree to a continuous map of physical and electrical reality.
So we had this new map where the math perfectly matches the physics of the chip. What impossible problems does this suddenly solve? What's the first big one?
The first one is global routing. This is a core task in chip design, connecting a set of pins with the absolute minimum amount of wire.
Which, in this world, is the rectilinear Steiner tree, or RST.
Right. And finding the truly optimal RST is famously an NP-hard problem. It's computationally exponential. You cannot search every possible way to connect the wires.
There are just too many possibilities.
Infinite, basically. But the Voronoi diagram gives you a geometric shortcut. The magic happens when you look at the diagram's vertices, the points where 3 or more of those cell boundaries meet.
Okay, what's special about those points?
Those vertices are the most probable locations for what we call Steiner points. They're the optimal places to create a junction to split a wire. The diagram basically screams, if you're going to build a junction, build it here.
So it takes an infinite search space and narrows it down to a handful of geometrically ideal candidates.
Exactly. It turns an intractable search into a simple, efficient checklist. It's a phenomenal speed up.
Okay, that's incredible for routing. What's the second application? You mentioned it earlier, signal integrity.
Right. The problem of crosstalk. As wires get packed closer and closer, they start to interfere with each other electromagnetically. They act like tiny capacitors.
And that interference can slow down signals, mess up timing, and even cause errors.
It's a huge cause of failure. And we already know the KV tree was useless here because it could place 2 interfering wires in totally different data structures.
Making the problem invisible.
Right. The Voronoi diagram, on the other hand, guarantees visibility. There's a simple rule. If 2 components share a Voronoi edge, a boundary, they are guaranteed to be geographic neighbors.
So a timing analysis tool doesn't have to search millions of wire pairs.
No, it just has to look at the boundaries on the map. The shared edge itself is a red flag for potential crosstalk. It gives you an instant definitive list of every single pair of nets you need to worry about.
That knowledge is crucial for hitting the high clock speeds we have today.
It's absolutely essential. And that leads to the third application, which is all about the bottom line, predicting manufacturing yield.
Yield being the percentage of chips that actually work when they come off the production line.
Yes. And a huge reason for failure is a random microscopic defect. a tiny speck of dust that causes a short circuit or breaks a wire.
So manufacturers need to predict how vulnerable their design is to those defects.
They do. And that involves calculating something called the critical area, the specific zone where a defect of a certain size will cause a failure. The old way to do this was with things like Monte Carlo simulations.
Which are slow and based on probability, right?
There you go.
Statistical sampling.
Exactly. You run massive simulations to get a good guess of how many chips will fail. But the Voronoi diagram gets rid of the guess. It calculates the critical area exactly.
How?
It uses its edges to define the skeleton of the empty space between wires. And the distance from any point on that skeleton back to the nearest wire tells you precisely how big a dust particle needs to be to cause a short circuit right there. It turns a statistical problem into a perfect deterministic geometric measurement.
So it sounds like this Voronoi framework isn't just one tool, but more like a flexible language for describing failures.
That is its great strength. You can create a whole family of these diagrams just by changing the definition of nearest.
Give me an example.
Well, if you're worried about a short where a defect connects two different wires, you don't care about the closest wire, you care about the second closest.
So you just build a map based on the second nearest neighbor.
Precisely. And that's called a second-order Voronoi diagram.
Look.
It partitions space based on the second closest feature, which is exactly what you need. For other problems, like a break, where a wire is cut, you use a different metric to model how a square-shaped defect would sever it.
That's amazing adaptability. But did this actually make it out of academia and into real-world commercial software?
It absolutely did. It moved directly into commercial electronic design automation, or EDA, tools. And the impact was, well, it was revolutionary.
Because the old methods, the statistical ones, were just so computationally expensive.
They were astronomical. You'd spend hours running simulations just to get a probabilistic answer. When a suite of these Voronoi techniques was built into a commercial tool, the shift from approximation to exact geometry changed everything.
What did that mean in practice?
It meant that instead of an hour-long simulation giving you a guess, you got a definitive, exact answer in minutes. The reported outcome was a performance improvement of over 60 times.
60 times, a 60x speedup, just by using a better map.
Just by aligning the algorithm's math with the chip's physical reality, it's a transformative leap in efficiency driven by pure geometry.
So what does this all mean?
It means the rectilinear Voronoi diagram is more than just a clever data structure. It's a continuous map of the chip's electromagnetic and physical world. It shows us that if you understand the hidden geography correctly, you can solve problems that seemed computationally impossible.
The efficiency we rely on every day isn't just from better materials, it's from better, more elegant geometry. Moving from those arbitrary KD tree boxes to this natural map of proximity saved exponential amounts of time.
It allowed designers to manage a level of complexity that was unimaginable before.
Which leaves us with a final thought. If a 60 times performance leap came from correctly mapping proximity in two dimensions, the flat X and Y plane of the chip, what comes next?
Well, tomorrow's chips are going vertical.
Three-dimensional.
Yeah.
With stat components, vertical transistors. The entire geometry of the chip world is changing again. So what new geometric maps of reality will we need to invent to understand distance and proximity in that complex 3D space? And what kind of performance leap is locked away, waiting for us to draw them?